we have already derived Laplace equation in the context of electrostatic potential. Let us see what interesting we can learn from Laplace equation, considering Laplace equation, because we did not already familiarize ourselves with solution of difficult differential equations. We will not go for a formal solution to Laplace equation, but we can still, without performing a formal solution to the Laplace equation, get many interesting conclusions based on the Laplace equation. We will try highlighting few of those. So, let us write down Laplace equation. Laplace equation is del square V equals 0 in a charge free region. If we consider an electric field, E as a function of the position vector r, that can be expressed as 1 over 4 pi epsilon naught integration r cap over r squared rho r prime d tau prime for a volume charge density. And if we try to calculate the potential right from the charge density, right from the charge distribution, we can do that, as we have already learnt, by V equals 1 over 4 pi epsilon naught integration over 1 over r rho r prime d tau prime. This way we can find this. Now, even this integral may be too difficult to handle it analytically. Now, if we have Laplace equation, that is this equation at hand in a source free, source charge free region, or say Poisson equation, that is del square of V equals minus rho over epsilon naught. If we have these two at hands, any of these, and appropriate boundary conditions, we can solve many interesting problems, and many problems that are much more difficult than whatever symmetry we have discussed so far. Let us write the Laplace equation in Cartesian coordinate system. We can write del 2V del x2 plus del 2V del y2 plus del 2V del z2 going to 0 in a charge free region. If we have this, then let us consider for simplicity the case of one dimension. In one dimension, we can write that d2v dx2 equals 0. Okay. By looking at this, we can, although with a set of appropriate boundary conditions, we can solve this, but we will not go in that direction. We would rather observe this equation and try to find out some properties of the solution to this equation. We would like to comment on the properties of the solution to this Laplace equation. One comment we can write is that if we consider a point, a line like this, where in between this point has a coordinate x and this length is a on this side as well as on left hand side as well as right hand side. So, this point's coordinate becomes x minus a and this point's coordinate becomes x plus a. Then for the solution, that is Vx at the midpoint here, is nothing but the average of Vx plus a and Vx minus a, because there is no charge in between. And this is valid for any arbitrary a as long as there is no charge on this segment that we are considering. And then Laplace equation solution cannot have any local maximum or minimum. Within our region of interest, we do not have any free charge, any charge in that region. Therefore, the solution to the Laplace equation cannot have local maximum or minimum within that region. We can move to 2 dimension now. In case of 2 dimension, we can write Laplace equation as del 2v del x2 plus del 2v del y2 equals 0. And this is no longer an ordinary differential equation, we get a partial differential equation in this form. So, we can consider in the Cartesian coordinate system x, y, z, a surface on this system, something say like this. This is a surface on this coordinate system, and the potential can be a continuous surface in x, y, v space. So, this surface can, if we consider a x, y and along the z direction, we have plotted the potential. This is 2 dimensional case. So, this surface that we have drawn here, that could well represent the potential without any local maximum or minimum in this case. So, let us also make comments in case of 2 dimensional situation. The value of the potential at any point is the average of those around that point. Value of V is the average from the nearby points. And the other comment that we can make is it has no local maximum or minimum. Let us move on to the case of 3 dimensions. In case of 3 dimension, we can write that the value of the potential is the average from the points nearby. That means the potential at point r with position vector r can be given as 1 over 4 pi r squared surface integral over a sphere VdA, where this sphere that we are considering has no source charge in it. And then the other comment would still be the same, that there would be no local maximum or minimum. In the absence of a free charge. Let us consider the average of the potential over a spherical surface of radius r. Let us try to show this thing explicitly. Here we have a sphere. Here is the center of the sphere. Let us consider this as capital R, and here is the surface element that we are considering. Let us consider a point charge q here outside the sphere. So, Laplace equation is valid in the sphere, and the distance from this point charge to the center of the sphere is z, and we denote this distance as r prime. Let us draw the x, y and z coordinates. This is x, this is y, this is theta in spherical coordinate system, and this element here is dA. If we have this, then the potential due to this point charge q at the surface element here can be given as V equals 1 over 4 pi epsilon naught q over r prime, r prime, this way, because the distance from q to the surface element is r prime. And r prime can be given as, looking at the geometry of this picture, z squared plus r squared minus 2zr cosine of theta. This is the same triangular rule. And then V average, the average potential is 1 over 4 pi r squared q over 4 pi epsilon naught integration z square plus r squared minus 2zr cosine of theta square root of this quantity. Oh, here I had a square, I missed it. Square root of this quantity, that is power, it is 1 over r. So, it is 1 over square root of this quantity powered minus half, and we have to multiply it with the surface element, that is r square r squared sin theta d theta d phi. And if we evaluate this integral, we will find this equals q over 4 pi epsilon naught 1 over 2zr z square plus r squared minus 2zr cosine of theta square root of this, and the limit goes from 0 to pi. that is the limit over theta, and then it becomes 1 over 4 pi epsilon naught q over z. This becomes the average of the potential. Now, this is precisely the potential due to this point charge q here at a distance z from the center of this sphere. So, if we average the potential over the surface of the sphere, we get the potential at the center of the sphere. So, in this example, we have verified the statement that we made here. So, we understand that our comment on Laplace equation is indeed valid.